Hello. This is an example homework video for exercise 9.4, number 21. This is discrete mathematics at Foothill College, spring quarter of 2025. I'm the instructor, Charles Wichorg. We're going to need the pigeonhole principle to solve this exercise, and here it is. A function from one finite set to a smaller finite set cannot be one-to-one. In other words, there's going to be at least two elements in the domain of the function that have the same image in the codomain. And we have a finite domain and a finite codomain. So that makes sense. A function has to map every element of its domain somewhere in the codomain. So if you have more elements in the domain than the codomain, then it's pretty clear that something is going to map to the same image. We're going to look at one problem, and as I already stated in the title, it's in section 9.4, and it's exercise 21. And it indeed will require the use of this pigeonhole principle. Here's the exercise. When 689 divided by 1493 is written as a decimal, what is the maximum length of the repeating section of the representation? So we need to talk about this. So what do they mean by the repeating section of the representation? Well, every rational number, and that's what this is, we have a non-zero integer over a non-zero integer. That's a rational number. Every rational number can be written as an infinite sequence of decimal digits. I'm not going to go into any proofs of that, but I think it should make sense to you. And sometimes the infinite sequence will just be repeating zeros. So if it's evenly divisible, you won't have any remainders. Other times it'll, a classic example is 1/3. If you write that out in decimal, it's going to be 0.33333 forever. Beyond some point in a decimal expansion, a sequence of digits will repeat forever. So that's what's going on here. That's the repeating section of the representation. Here's an example. If I give you the rational number 3 over 14, or 3 divided by 14, if I do this division, if I do long division on this pair, here's what I get. 0.2142857142857. And this one's fairly easy to see that we have some kind of repetition going on here. If I highlight it, you'll see that the 142,857 repeats over and over and on forever. The length of this repeating section is the length of the sequence of repeating digits that they're talking about. So in this case, we have a length of 6, right? 1, 2, 3, 4, 5, 6. 6 digits, a sequence of 6 digits, begins to repeat and then continues to repeat forever. So let's go a little deeper on this, and let's consider a simpler example. Let's take the rational number 3 divided by 14. And then we'll use long division on this to see how this is all going to work out. So we're going to divide 3 by 14, and that's going to calculate the decimal expansion of the rational number 3 over 14. And here we go. I'm going to walk through it. I want you to be aware of a cascade of remainders. So we're going to keep getting remainders as we keep doing the long division. And there'll be these unending small division steps that'll generate quotient digits. You'll see in a minute. Alongside, on the right side of the page that I'm going to show you, there's going to be a list of line numbers so that I can reference the lines. And as the division proceeds, I'll also put in there a list of remainders that are appearing. And that'll also be on the right side of the page. So let's get started. We want to start with 14 dividing into 3. So here's our classical long division setup. We have this, I don't even know what you'd call this sign, this kind of like two sides of a rectangle, just to emphasize on the left we have the 14, that's the divisor, and the 3 inside is the dividend. This vertical line I've put here says that the decimal point starts there. That's just to keep that in our mind. These two are integers, but when we're dividing, we're going to have to move into the decimal territory. Okay, so 3, we can write that as 14 times 0 plus 3. we're using a quotient remainder theorem. 14 times 0 plus 3. So 3 is less than 14, so we can't take any 14s. We have to have 0 of them, and 3 itself is its own remainder. So that's what we have here. And you notice here's the column with remainder, R for a remainder. I now have a 3 under it. Our first remainder is 3. Now we're going to continue in the ways of long division, and we're going to extend the remainder with a 0 decimal place. You can see that up here I have 3 and then a 0, so I now have a 30. And I'm going to divide the 14 into the 30. So we couldn't divide into 3. I'm going to try and divide it into 30, and it will work. And 14 times 2 plus 2 will equal 30. So we still have a remainder of 2, and we have a quotient digit of 2. And I write that up here, the quotient digit on the top and the remainder on the bottom. And I entered the remainder 2 in the column, the R column. Okay. Now, again, with long division, we just keep going. And until we get a remainder of 0, we keep working. And in many cases, we'll never get a remainder of 0. And that's where we get these repeating quotient strings. Well, anyway, we put a 0 on here. We extend with a 0 up in the quotient, the dividend line. And we extend the remainder with a 0. So we have a 20 now. So now we're going to divide 14 into 20. And 20 is equal to 14 times 1 plus 6. So it's a remainder of 6, a quotient digit of 1. We're going to do the same procedure. I put the 6 in the remainder column. I'm going to now extend that remainder 6 with a 0. And I'll extend a 0 on the top here. So I now have a 60 to be divided by 14. 60 is equal to 14 times 4 plus 4, so the 4 is the remainder, the 4 is also the quotient digit. So far we've got 0.214 and with a remainder of 4. But we're going to continue. We're going to extend the remainder with a 0, and up in the quotient we'll also put a 0. So now we're going to be dividing 14 into 40. And that's going to be 14 times 2 plus 12. 14 times 2 would be 28. 28 plus 12 should be equal to 40. So here we have a 2-digit remainder. It's no problem. We're going to extend that one with a 0, and we're now going to be dividing into 120. We extended the 12 with a 0 appropriately, and our quotient is 2142. Let's see what we're going to get from here. Dividing 4 into 120, we get 120 is equal to 14 times 8 plus 8. We have a remainder of 8, a quotient digit of 8. So you can see the quotient digit up here and the remainder down here. We're going to extend the remainder with a 0. So we're going to be dividing 14 into 80. Okay, now 80 is equal to 14 times 5 plus 10. So there's a remainder of 10 now. And we put the 5 up in the quotient position. And now we're going to be dividing, we're going to extend the 10 with a 0. So we're going to divide 14 into 100 now. So we're always doing this extension with a 0, the remainder with a 0. And if we're dividing 14 into 100, we know that 100 is equal to 14 times 7 plus 2. So we have a remainder of 2. Our quotient digit is 7. We're going to extend again with a 0. So we're going to be dividing into 20. So far we have 0.2142857, and now we're going to be dividing into 20. But now we need to notice something. We need to notice that we're going to repeat the dividend of line 4. We had a 20 up here on line 4 that we divided 14 into, and we ended up with... if we go back, we're going to subtract a 14 from 20, and we're going to get a 6 as a remainder, right? We remember we did it. The same thing would happen here. We'd have a 14 to subtract from the 20, we'd get a 6 as a remainder. I hope you can see that we're going to repeat what we did from line 4 down. The 20 is going to generate a remainder of 6. That's going to turn into a 60, which will generate the remainder of 4, which turn into a 40, generate the remainder of 12, on and on and on. Here's our repetition. So the remainder of 2 on line 16 causes the repetition of the quotient digit in the next division. I don't show the next division, but you get this quotient digit 1. So here you can see the repetition beginning. We have 0.2142857, and this is going to repeat now. We could predict now the next digits are going to be 42857, 42857, going on forever. This is the repeating sequence. So from this point onward, here's the sequence that's going to repeat. I'm sorry, the remainders. So we're looking at the remainders at the moment. Notice the remainders are repeating. 2, 6, 4, 12, 8, 10. I'm going down the column. 2, 6, 4, 12, 8, 10. It was that repetition of that remainder that started the repetition up here. So the quotient will repeat the sequence 142857, as I mentioned before, and that'll go on forever. But it's the remainders that are causing that. So the repetition of the remainders creates the repetition of the quotient digits. So it's the remainders are important in figuring out what the length is going to be of this repeating quotient sequence. So let's ask ourselves, why must the remainders repeat? And it's a fairly simple answer. For a divisor of n, there are going to be n-1 distinct non-zero remainders. There'll be n if it counts 0. The non-zero are going to be 1, 2, 3, all the way to n-1. After we use these n-1 distinct non-zero remainders, by the pigeonhole principle, a remainder is going to repeat. Now we may see a 0 come up, or if not, we're going to repeat one of these non-zero remainders. Let's look at that closer. If we had the case where we found a remainder of 0, then all future remainders and quotient digits would be 0. Right? They would have no remainders, everything would go out to 0. So in the length of the repeating sequence of quotient digits would not be bounded. It would just be 0, 0, 0 forever. But that's not the case we're interested in, right? We're looking for a repeating sequence beyond just 0. In other words, we're looking for non-zero remainders. All future remainders and quotient digits are going to follow an unbounded repeating sequence, okay? Because once we repeat one of them, you can see that it'll generate the same dividend, and that will generate the same remainder that we already saw, and it'll go on in the same way. And the length of the repeating sequence is going to be the length of the sequence of repeating non-zero remainders. So the remainders are very important. And this gives us that the maximum number of non-zero remainders is the maximum length of the sequence of repeating quotient digits. So we can figure out the answer to this problem by looking at the maximum number of non-zero remainders. So let's revisit the question. They're asking us, when 683 is divided by 1493, when that's written as a decimal, in other words, this is a rational number, when this rational number is written as a decimal, what is the maximum length of the repeating section of the representation? We can answer that. The longest sequence of quotient digits will be generated by the longest sequence of non-zero remainders. And when we divide an integer n by 1493, there are going to be 1,493 possible remainders if you include 0, 0, 1, 2, all the way up to 1492. But the 0 remainder is off limits for us. We're not going to use that because that's going to end up giving us some repeating zeros forever. So we're not interested in that. So we're going to say that the maximum length of the repeating section of the representation is going to be 1,492 digits. Right? We ignore the 0. 1,492 digits. But let's think about this. That's a maximum. That's the maximum number of remainders that you could put in the sequence without repeating one of them. After you get to 1492, you're going to have to repeat one of these. So we can ask, for this rational number that they gave us, how long is the actual repeating section? Because maybe it's not this long. That's a big number, right? So I used an online calculator to find the answer. I went online to something called the Big Number Calculator. And I asked it for a precision of 1,500 digits after the decimal place. to get us beyond the 1492, 1493. And I divided 683 by 1493. And here's the result. So I'm very glad I didn't try to do this by hand. Right? I'd never get done. I'm just showing you in red here that it looks like we do have the repetition. Way down here on the bottom, we have the 4, 5, 7, 4, 6, 8, 1, 8. That's how this starts. 4, 5, 7, 4, 6, 8, 1, 8, and then it goes on. So this is the cutoff at 1500. I could go farther to see if indeed it continues following this, but I'm going to just assume, and I did a few calculations lowering the precision, and it seems to me that the length of the repeating section is 1492. It seems like the textbook went out of its way to find a combination that worked that way. To really be sure, I'd need to calculate the remainder repetition, and I just don't want to do that. And this tool didn't offer to show me the remainders. We'd have to see the sequence of remainders and see that they don't repeat until 1,492 positions. Okay, so why this problem? It's it advertises the pigeonhole principle and shows you where it's good in an abstract problem. If we tried to find this repetition, this maximum by hand calculation, it would be pretty much impossible if we did by paper. It also shows us the discovery of a quotient is with a very long repeating pattern, right? This one didn't indeed have that long repeating pattern, and so they do exist. And it sent me, and I presume you as a student will be looking for a high precision calculator software to help you out. We're at a point in mathematics where we aren't going to do things on paper for larger problems, and we're trusting the machines to give us the correct answer. All right, that's it for this one. Thank you.